So we've learned how to write the names and formulas for our simplest ionic compounds. Now we're going to look at how to write names and formulas for ionic compounds that contain transition metals or metals that can have different charges. So with our simple ionic compounds, our metals always had the same charge. Sodium always has a charge of +1. Calcium always has a charge of +2. Those we can get right off the periodic table. When we get into the transition metals and some of those other metals in the P block, those metals can have different charges. So when we write their names and formulas, we have to take that into account because we can't predict the charge of the metal just based on their location on the periodic table. So our general rules are still the same. The rules for the order that we write the names or the formulas is still the same as it was for our simple compounds. It still goes metal, then nonmetal. So it's still our positive, then our negative charge. The ending is also still the same. You take the end of the name of the nonmetal, take it off, and add IDE. So you're still changing the ending to "ide." The difference here with the charges, so the charges still have to balance. On our metal, we're going to find the charge for our metal from a Roman numeral. Our nonmetal, we're still going to find off the periodic table. So the difference here, our charges have to balance, but we're going to find the charge for our transition metal from the name in the Roman numeral, not from its location on the periodic table. Let's jump in and look at some examples and make sense of all of these rules. We're going to write names first. So I have 3 formula examples, and we're going to work backwards and we're going to write the names for these compounds. So this first one has iron and oxygen. So the oxygen we know is going to be oxide. Same from our previous types of ionic compounds. So you take oxygen, take off the end, and change it to IDE. So we have oxide. And then iron is still going to just be iron. But the difference with our transition metals is we have to add a Roman numeral here in between our metal and our nonmetal to indicate what charge the metal has. So let's figure out what charge iron has. So remember, our charges had to balance. And before we looked at these as crisscrossing. So if my iron has a subscript of 2, that means it was originally the superscript or the charge on oxygen. Now that makes sense. Oxygen, based on its location on the periodic table, has a -2 charge. The 3 then, that's the subscript for oxygen, is going to come back up here and be the positive charge on the iron. So iron has a +3 charge, oxygen has a -2 charge. If we were to work backwards to do our formula, we'd crisscross them. The 2 goes down to the iron, the 3 goes down to the oxygen, and we get what we originally started with. So our iron has a 3 charge, a +3 charge. So that means we're going to write a Roman numeral 3 in parentheses between the iron and the oxide. This tells whoever is reading the name of this formula that iron has a +3 charge, and then oxygen's still the same. Let's look at our next example. So we're still with iron and oxygen, so it's still going to be oxide. But we have a different formula this time, so we have to figure out what that charge is on iron. Well, we don't know the charge on iron, but we do know the charge on oxygen. Oxygen has a -2 charge. That's because of its location on the periodic table. We know that oxygen has a -2 charge. In order for our charges to balance between the iron and the oxygen, we have 1 iron and 1 oxygen. That means our iron must have a +2 charge. If one oxygen has a -2 charge, and we have 1 oxygen and 1 iron, iron must have an equal charge. If we take what we have here and work backwards to write the formula, the 2 would go here, the 2 would go here. We'd end up with Fe2O2, which we know reduces to FeO, which is what we originally started with. So iron in this case has a charge of 2. So notice here, it is important to note whether the iron has a +2 charge or a +3 charge, because that makes a profound difference on the formula for the compound. Okay, Let's look at our last example. So we have copper and we have fluorine. So we're going to write copper. We know we're going to have something in parentheses. Fluorine is going to change to fluoride. Now let's work backwards. Fluorine, we know, has a -1 charge. That's because of where it is on the periodic table. We know fluorine has a -1 charge. We have 2 fluorines, so we have a total of -2, which means copper must have a +2 charge. We have 2 fluorines in our formula, which gets us a total of -2 because each fluorine has a -1 charge, which means copper must have a +2 in order to have 1 copper with 2 fluorines. Again, if we work backwards, if we take this 2, that would go up with copper, so there's our +2. We can imagine that there's a 1 down here next to the copper, which would go up with the fluorine, which is what we know fluorine's charge is. We know fluorine's a -1. So that leaves copper with our +2, which means we'll write a Roman numeral 2 in that parentheses. And we read this as copper 2 fluoride. So now let's go from the names of the compounds and let's write the formulas. So we have nickel 3 chloride as our first example. So nickel is Ni. Remember, this 3 tells us the charge for our nickel, so it's a +3 charge. Your metal is always going to be a positive charge because metals lose electrons. Metals are always positively charged. And chloride is chlorine. If we look on our periodic table, it's in the column over here, so that's our -1 charge. If we crisscross our charges, we end up with nickel, chlorine, and we have 3 of them. So NiCl3. So the 1 went down with the nickel, the 3 went over with the chlorine. So nickel 3 chloride would be NiCl3. Let's look at our next example. Let's look at tin. Tin is on the periodic table. It's not technically a transition metal. It's over here in our other metals. But for our purposes, we're going to treat it as a transition metal because tin can have different charges as well. So tin's symbol is Sn. The Roman numeral 4 tells us it has a +4 charge. Iodide is the element iodine. Iodine has a -1 charge. If we swap our charges, we end up with SnI4. So tin 4 iodide would be SnI4 because we crisscrossed our charges. Our tin had a +4 charge, so that becomes the subscript on the iodide, and our iodine had a -1 charge, so that becomes the unnamed subscript on the tin. Last example, let's look at cobalt 3 phosphide. So cobalt is Co. The 3 tells us it has a +3 charge. Phosphide is phosphorus. We find phosphorus on our periodic table. It's in this column right here, so that has a -3 charge. So phosphorus has a -3. Now, since they're equal, we know that we're going to have 1 cobalt and 1 phosphorus. If we crisscrossed our charges, we would get CO3, P3. But remember, we want our most reduced form of our formulas. It's kind of like reducing fractions. If you had a fraction of 3/3, you'd reduce that to 1. Same thing with this. If we have cobalt 3, phosphorus 3, we're going to have 1 cobalt, 1 phosphorus because they reduce down. We have 2 main things that we need to remember when we look at writing names and formulas for transition metals. The first thing is that if there's a transition metal, we have to remember that the Roman numeral tells you the charge. So in the name, the Roman numeral is going to tell you the charge on the metal. That means that you have to include the Roman numeral when you write the name. Otherwise, we don't know if iron's going to have a +2 or a +3 charge. They're 2 very different compounds. So you have to include the Roman numeral when you write the name. And when we're writing formulas, the Roman numeral is going to tell you the charge on the metal. Everything else follows the same rules as it did with our simple ionic compounds.